Hello, welcome to my talk all about the fluids. This talk is the first part on an interesting and important topic. Is the Navier-Stokes equation correct? In this talk, the focus would be on the inconsistencies of Navier-Stokes equation, the well-known universal governing equation for fluid motion. However, some recent research work and the effort for understanding the physics involved in the Navier-Stokes equation have shown the inconsistencies behind the Navier-Stokes equation. For instance, the Cauchy symmetric stress tensor of solids had been fully adopted to fluids by Cauchy himself nearly 200 years ago. But this requirement may not be a prerequisite for fluids as that for solid, since fluids are fundamentally different from the solids. The fluids flow under applied shear stress, but the solids do not. In this talk, I will show you what are the inconsistencies behind the Navier-Stokes equation, based on the direct physical analysis of fluid motion and the examples from the famous textbook. Is the Navier-Stokes equation correct? This is quite a scary question. Nobody would expect an answer no, because the Navier-Stokes equation had been accepted and practically valid for nearly 200 years, since Navier first formulated the four-fluid dynamic equation in 1822. Stokes presented an elegant derivation of the fluid dynamics equation in 1845. But I would say here the answer to this question is yes and no. I will tell you the reason why I say this. For years, that's because the Navier-Stokes equation as the governing equation for fluid motion has been proven by numerous examples, experimental data, analytical solution, and numerical solution. For no, it is because we have already seen some inconsistencies behind the Navier-Stokes equation, specifically on the symmetrical stress tensor for fluids. It is well known the Cauchy's symmetrical stress tensor was originally developed for elastic materials, the solids, and then fully adopted to the fluids by Cauchy himself in 1827. However, I will show the inconsistencies regarding the symmetrical tensor for fluids. For instance, how we can explain the vertical stress tensor in the Couette Flow, how to explain the viscous shear stress in the pure rotating motion of fluid, why the factor 2 is added in formulating the symmetrical stress tensor but without the physical basis. And in some textbook, it is clearly shown that there are examples where the symmetrical stress tensor is not satisfied in some real flows. How we can explain these inconsistencies? In this talk, I will show you the details of all these inconsistencies. In the next two slides, I will show you how the Cauchy symmetrical stress tensor have been derived. It must be noted this is basically for solids, not necessary for fluids. Consider a small element as shown in the figure, and the stress tensor pairs which could produce the moment in x direction are shown in the figure, and the stress pair are the tau 23 and tau 32, and the tau prime 23 and the tau prime 32. If the element is very small, the stress tensor component on both sides are equal. For instance, tau 23 equals tau prime 23, tau 32 equals 2 tau prime 32. The moment due to the stress couple tau 32 and tau prime 32 is in x direction, so delta m x1 equals this because of the stress pair tau 32 and tau prime 32. Similarly, the moment due to the stress couple tau 23 and tau prime 23 would be in negative x direction, so we have delta m x2 given by this. Put this together, we got the total moment in x direction, delta mx, given by this. Because of the moment acting on the element, so its rotation motion around the x-axis would be given as this. For this element, the moment of inertia for the element given delta I xx as this. So put this into the equation, we can calculate the rotation acceleration omega x dot as this. So if the element becomes infinitesimal, that is, delta y and delta z are both close to 0, so the rotating acceleration would become infinite unless tau 32 equals tau 23. Similarly, we can prove tau 12 equals tau 21 and tau 31 equals to tau 13. This is the Cauchy's second law of rotation motion for solids. The stress tensor must be symmetric, and this law is then fully adopted to fluids by Cauchy himself. The concept of the symmetric stress tensor for fluids have been widely accepted ever since. However, consider the fundamental difference between the fluid's motion and the solid's motion. Can we ask a question? Is this symmetric stress tensor a prerequisite for fluids? In this slide, the difference of a shear stress applied on a solid element and a fluid element is shown. Consider the small cube and apply a shear stress tau 23 on the element as shown in this figure. If the element is a solid and elastic material under the applied shear stress, the element would deform and thus a shear stress tau 32 would be produced, which could balance the applied shear stress due to the elasticity of the material. This is the requirement from the Cauchy symmetric stress tensor, as tau 23 must equal to tau 32. However, if the element is a fluid and the applied shear stress will cause a flow in the shear stress direction as seen here, and due to the flow in the fluid, a friction is induced which could balance the applied shear stress in a steady flow. Therefore, there will be no additional shear stress to balance the applied shear stress as seen in the solids. This fundamental difference can be understood. A fluid could have a translation or rotation motion or both as those for a solid, but a fluid may also have a flowing motion, while the solid does not. Now we look at the first inconsistency, Q1, in the simple classic Couette flow. The Couette flow is confined between two large parallel plates of a distance h. The bottom plate is fixed while the upper plate moves at a constant velocity u0. The moving velocity of the upper plate is small, hence the flow between two plates is assumed to be nominal. Such an assumption is for an analytic solution for the Couette flow. Based on the analysis of the flow, we can see there should be no fluid velocity in y and z direction. Both v and w are 0, and u is the function of y only. As such, the Navier-Stokes equation can be simplified into this partial differential equation and apply the no-slip boundary condition at both plates. The solution is given as this, and the plot of the velocity profile is seen as this. The flow velocity increasing linearly with y. This classic flow solution can be found in many textbooks, and the correctness of this solution have been validated using experiment data. Now we can calculate the shear stress in the Couette flow. We can draw a small rectangle, and there will be 4 stress components as seen in here. And based on the requirement of the Cauchy symmetric stress tensor, we have tau12 equaling to tau21 and tau prime 12 equaling to tau prime 21. And the horizontal shear stress based on the Cauchy symmetric stress tensor is given as this. This non-zero horizontal stress can be easily understood. It acts in x direction on the surface of a constant y, and it causes the horizontal flow. Based on the requirement of the symmetric stress tensor, tau21 equals to tau12. Hence, in the Couette flow, the vertical shear stress component tau21 is given by this, same as tau12. Both are non-zero. Now we look back at the definition for fluid. A fluid cannot bear any shear stress at rest, and under shear stress, the fluid flows in the direction of the applied shear stress. Therefore, it is easily understood that the non-zero horizontal shear stress tau12 causes a horizontal flow. Upon the requirement of the symmetric stress tensor, the vertical shear stress tau21 is non-zero, same as tau12 in the Couette flow. But why this vertical shear stress tau21 does not cause a vertical flow in the Couette flow? If based on the fluid definition, in the Couette flow, we have a non-zero horizontal shear stress tau12 due to the horizontal flow, but the vertical shear stress tau21 must be 0 because there is no flow in the vertical direction in the Couette flow. Therefore, tau12 should not equal to tau21. That is, this classic Couette flow has shown that the flow stress tensor can be asymmetric. It may be argued that there may be a vertical stress tensor, but the wall the upper plate has stopped a vertical flow due to tau 21. We can imagine that there may be a flow coming out. If we make an opening on the upper plate like this, is this true? The answer for this is no, because whether there will be a flow coming out from the opening on the wall totally depends on the fluid pressure, not the vertical shear stress. If the flow velocity is large enough, based on Broglie's principle, the pressure in the flow would be low, and hence there might be a suction of the flow through the opening, rather than an outflow through the opening. We can examine the flow in this figure. If the non-zero vertical shear stress exists in the horizontal pipe, it will cause a continuous flow in the small tubes, regardless of how high of the small tubes. In reality, the water level in two small tubes can never be higher than the water level H0, and the height in the small tubes only depend on the pressure in the pipe. Obviously, in such an opening, the so-called vertical shear stress does not exist. Thus, this proves that there is no vertical shear stress in the Couette flow. This conclusion can be also applied to the Hagen-Poiseuille flow, a laminar flow in a long horizontal pipe. Therefore, the requirement of the symmetric stress tensor is not a prerequisite for fluids. The second inconsistency, Q2, would be whether there will be viscous stresses in the rotation motion of fluid. Based on the classic book, Marine Hydrodynamics, it states there will be no viscous force if the flow moves as a rigid body without deformation, or fully follow the velocity description as this. Here, vector V0 and vector omega are the vectors for translation and rotation velocities, and the vector r is the position vector from the origin of rotation. Viscous stresses would be produced only when the fluid motion differs from the above equation, which would be the deformation or the flow of the fluid. Consider a rotating solid cylinder shown in this figure, which rotates evenly along its axis. For such a rotating solid, there will be no shear stress acting on the solid. That's why the rotating motion is excluded in the calculations of the shear stress in solid. For the rate of strain in fluids, it can be generally decomposed into two parts, as this. Stokes himself did the same decomposition in 1845. The symmetric part is the shear or angular deformation, and the anti-symmetric part is the rigid body rotation. Based on the principle mentioned in the previous slide, the rigid body rotation would follow the velocity description by this formula. Obviously, the shear deformation would be different from the velocity description by this. As such, the shear deformation could contribute to viscous stress, but the rotational term would not contribute to the viscous stress. This is why it is excluded in deriving Navier-Stokes equation. Is this true that the fluid has no viscous stresses if it rotates like a rigid body? let's look at the special Taylor-Couette flow. The Taylor-Couette flow is confined between two coaxial cylinders with radii of R1 and R2, and these two cylinders could rotate at different speed, omega-1 and omega-2. This is the setup Couette used to measure the fluid viscosity. We can assume the cylinder rotation speeds are small, thus the flow between two cylinders would be laminar, and hence we can find an analytic solution for such a flow. Now we can consider a special case, omega-1 equals to omega-2. The two cylinders rotate at the same rotating speed. Thus, in a steady state, the fluid would be rotate follow the two cylinders like a rigid body, and the flow azimuthal velocity would be given by this. Here, omega is the rotating velocity of the cylinders, and r is the radial position from the central axis. Obviously, at different radial position, the fluid velocity would be different. See U1 and U2 here. Thus, there will be viscous stress. Calculate at this. Obviously, it is non-zero. This proves that in the pure rotational motion, the fluid would produce the viscous stresses. This is very different from the rotating solid. The third inconsistency, Q3, would be the formulation of the symmetric stress tensor. Similar to solid mechanics, the fluid motion might generally be described as follows, or their combinations. Translation motion, which means the fluid element moves from one position to another without dilatation or distortion. Dilatation, the fluid is compressed or expanded, but without the distortion. Distortion, it is a combination of the rigid rotation and the shear deformation of the fluid element. All these three types of motion can be found in the reference books: boundary element method, aerodynamics for engineering students, and the fluid mechanics. However, for a fluid, based on the definition of fluid, it flows if a shear stress is applied, as seen in this, and the flow would flow as this. And since the fluid flows, the fluid viscous force would balance the applied shear stress in a steady flow, given by this. In the original derivation of Navier-Stokes equation, as it has shown that the fluid distortion can be decomposed into the rigid rotation and the shear deformation, but the only symmetric rate of the shear strain could contribute to the viscous shear stresses, as the rate are given as this for the X and Y direction, and this for other rates of the strain. Based on the Newton's formulation for fluid viscous stress, which would be proportional to the rate of strain, therefore, the stress tensor of correct physics would be calculated as this. But this stress tensor would not lead to the correct Navier-Stokes equation. Instead, the symmetrical stress tensor has to be formulated as this. Stokes did the same in 1845, in which the artificial factor 2 must be added to the formulation. However, the question is, the factor 2 has no physical foundation. In the book, Aerodynamics for Engineering Students and the Boundary Layer Theory, both give similar explanation. The factor 2 is merely used for convenience, so as to cancel out the factor 1/2 in the expression of the rate of shear strain. But this formulation is physically incorrect. The problem is actually caused by the adoption of the symmetrical stress tensor for fluids, where the part corresponding to rotation has been wrongly taken as the non-contributor to the viscous stress. In fact, the shear stress tensor can be asymmetric for fluids, and it would not cause the fluid spinning as we see in the solids. This is the illustration for a fluid element. If a shear stress tau 3 is applied on the element, the fluid flows simply like this, and the viscous forces would balance out the applied shear stress. The fourth inconsistency, Q4, would be the exceptions for the symmetrical stress tensor for Navier-Stokes equation as we had in real fluids. In the book of Kondo, Cohen, and Dowling, Fluid Mechanics, on page 126, there is a statement as this: the stress tensor symmetry is violated in the electric field on polarized molecules, where anti-symmetric stresses must be included in the analysis. Another example is in Wilcox's book, Turbulence Modeling for CFD, on page 39. It is stated the symmetrical stress tensor is for simple viscous fluids, but not for some anisotropic fluids. However, there is no reason given for this claim. Hence, we can ask a question. If the Cauchy's symmetrical stress tensor is universally correct for fluids, then how we can explain the exceptions we found in the real fluid? After all, we never see any exceptions for Newton's laws of motion. In this slide, the summaries would be given. The classic Couette Flow has shown that the shear stresses can be asymmetric for fluids. There will be viscous stresses in the pure rotation motion of fluids. Therefore, ignorance of the viscous stress due to the rotation motion would not be physically consistent with the facts. The original form of the symmetric stress tensor has a factor 2, which has no physical significance or foundation. In the real fluids, there are exceptions for the symmetric stress tensor. Why have such exceptions for the universal correct law? Having talked about all these inconsistencies, the Navier-Stokes equation itself is correct, especially for the incompressible flow. The second part of the talk will discuss the solution to all these inconsistencies behind the Navier-Stokes equation.